Okay, so I guess we can start. It's a pleasure to have Gérard Besson for Grenoble, and I will say a few words about his CV. So he was a student at École Normale Supérieure, and he took his PhD with Marcel Berger. Then he started with as a research fellow at École Polytechnique, and eventually was hired at CNRS. First as in Grenoble as attaché de recherche, and then chargé de recherche, then director of research at CNRS. Sorry for my French. So he got several prizes, like the Alexandre Ioannidis Prize of the French Academy of Sciences, a grant from a Clay Mathematics Institute, and an ERC grant recently. He was a supervisor for 14 PhD students, and then chairman of the Institut Fourier in Grenoble for 5 years, member of the administrative board and of the scientific board of IHP in Paris, and also of the scientific board of the Institute of Mathematics at CNRS, and also member of the board of mathematical sciences publishers in Berkeley. So thank you, Gérard.
Can you hear me correctly? Okay, thank you very much. So I guess the microphone is for the people who are online. So first of all, I should say that I'm really honored to be here because I admire the work of De Giorgi and many other people here in this room, of course, but it's very important for me. So I will be talking about this subject. And here is a list of my collaborators, one of whom is very close to here, Andrea Sambusetti from Roma. And the others, Gallo is retired, but he's in Grenoble, and Courtois is in Paris. And I want to talk about groups, which is unusual for Riemannian geometers. Okay, so it's a colloquium talk, so I have to be to explain the things, and I will start in a brutal way, and I apologize for that, and then I explain the rest of it. So the talk is about finitely generated, what we call Mark groups. So gamma is a group. It is finitely generated, so it's some kind of countable group. And sigma is a finite generating set. And that's my main object in this story. And this generating set, we usually take it to be symmetric, meaning that if an element gamma is in the set, then its inverse is also in the set. For practical reason, it is not meaningful at all mathematically, but it's very practical. And I want to talk about this result. Well, so you give two numbers, and the result says that there are finitely many non-cyclic torsion-free delta hyperbolic Mark groups satisfying this inequality, where Ant stands for entropy, and this up to equivalence. So as I told you, it's very tough to start a colloquium with this kind of result. And the rest of the talk, I will explain all the words. And maybe in 40 minutes, we'll understand the context and understand what is the question behind this. So you can forget about the statement, but you have to remember for the rest of the talk that we want to count groups. And the question that you may ask yourself, which I have asked myself, is how do we count finitely generated groups? Satisfying some properties, which I will define later. So first of all, I have to set up the context in which this work takes place. And it's not the context of Riemannian geometry, but of metric spaces. So let me start by saying a few words about the metric spaces we are interested in. So this space, I will be considering a metric space, X, D is the distance, which I assume to be proper geodesic. So let me define these two words. So proper means that closed balls are compact. So somehow it's locally compact, which is a pity because there are interesting metric spaces which are not locally compact, for example, built on Banach spaces, but we miss them in this result. And essentially because the result would not be true in this context. And geodesic, so let me define what is a geodesic in this context, not defined by a second order differential equation because this is a metric space. So just a map from an interval of R into the space which is such that between C of t and C of s, the distance is just given by difference between the parameters. And so all geodesics in this talk are minimizing, not locally minimizing, completely minimizing, right? And so a space is said to be geodesic if any 2 points in X are joined by at least one geodesic. And the whole story is in at least, there might be several. Okay, so I don't want to spend too much time giving examples, but there are plenty of examples. So the standard one are just Rn and the Riemannian manifold, but one could also consider metrics on CW complexes or triangulated objects and these kind of things. But I will give the main example in a few minutes for this talk. Right. So I will add now a piece of information that we need for the rest of the work. And so we start with this proper geodesic space. And we'll have group acting by isometry. So the isometric group of a metric space might be completely empty, like for Riemannian manifold, but I assume that it's not the case. And there are isometries, and I will consider discrete subgroup of the group of isometries. Discrete meaning that it's discrete. So the orbits are discrete subsets and so on and so forth. Very elementary situation, right? And even more elementary, I assume that there is a compact quotient to the space. And there are plenty of examples of this situation. I'll give one later, right? I add one piece of information. We need so if you think as a Riemannian geometry, there is the metric which gives rise to a distance, and then there is a canonical measure which is called the Riemannian measure. So I'm sorry, I'm doing parentheses for the people who are familiar with the Riemannian geometry. If you are not, just forget. So here I want to add a measure. So it's supposed to be locally finite, non-trivial, a Borel measure, and invariant under the action of the group, of the isometry group. Well, at least on the subgroup gamma here. And so I can define one word which would, yes? What, excuse me? Yes, because gamma is included in the isometry group. So isometry, just meaning the distance is preserved. But if you have any question, don't hesitate, right? And I can define now one of the words that was in the statement, which is this notion of entropy. So it's called entropy because it's closely, on Riemannian manifold, it's closely related to the dynamics of the geodesic flow. So it's a physical kind of object. But for us, it's just defined by this remark. So you look at the volume of these balls, but how do you measure the balls of radius r around some point x? But how do you measure the volume? You can use this measure that we have at hand here. And you take, we always think as people familiar with negative curvature, where balls in negative curvature have a tendency to grow exponentially as far as volume is concerned. So exponentially means exponentials of some constant times the radius, and we want to capture the constant. So to do this logarithm and divide by r and look at the limit when r goes to infinity. Right. So the limit may not exist, but in the case where we have compactness here, it does. It might depend on x, but again, here we can easily show that it does not depend on x. So it's really a number which is associated to this situation. And as you can see, it is asymptotic. It's a limit. So the natural question is, what can we do with this? I mean, it's not clear that it's useful. So for people who are familiar with Riemannian geometry, let me make a comment. Oh, and so one of the assumption is that we will be considering metric spaces such that this number is bounded above by some constant, which I assume to be strictly positive because it's more convenient. So in blue, I put the assumptions when it appears in the context, right? So far, it's elementary. So again, it's a parenthesis for people who are familiar with Riemannian geometry. As an example, if one takes a complete Riemannian manifold whose Ricci curvature is bounded below, then the entropy is bounded above. So let's give an example. Why do I mention this curvature stuff in the context of a metric space? Well, curvature, whatever it is, so I choose here the, how can I call it? The Italian curvature, right? And this is the one which is useful in this context. And curvature is something you compute locally, and it's something which is infinitesimal. So it's an infinitesimal information on the space. And this means that at every point, this inequality is satisfied. Whereas this inequality is asymptotic. And so in view of this relation here, we will consider this edge as a good replacement of a lower bound on the curvature. But of course, this is asymptotic, so we lose something. And the game to play is to understand what we can do with this and what we have lost. And this will be the discussion that I will have later. Right, so if you are not familiar with Riemannian geometry, you can just forget this. But it's like a Gaussian curvature on a surface, an infinite surface. And so I mentioned a measure, but let me give you one simple example. And this is the one example that we will be working with during the whole talk. This is a counting measure. So well, it's not one measure, it's a family of measure. You pick a point, you look at the orbit of the point under the group capital gamma, which is a subgroup of the isometric group, and you put a Dirac mass at every point, and you sum up. It's locally finite because the group is discrete. So on a ball, which is compact, closed ball, which is compact, there are finitely many points of the orbit. So here, the two hypotheses, gamma discrete and the space being proper, comes into play, right? So again, this is very weak as a measure. I mean, just count number of points which are in balls, points of the orbit. But so what can it be useful for? This is the question. And I will try to describe how we can use that. Now you can forget about measure. We'll only take this into account. Of course, for every point x, there is one measure, but x will play no role in the story. Okay, so let me give you the main example of metric space that we want to consider. So again, if you consider a finitely generated group with a symmetric finite generating set, one can construct a graph, which is a well-known object, but let me recall it. It's called the Cayley graph of the group. And it is constructed as follows. So here I insisted to have a board, so I have to use it now. So the vertices of the graph are the element of the groups, and there is an edge between two vertex if one is deduced from the other by the action of an element in the generating set, right? So you start with the identity element, you apply, say, S1, say you have two element generating set, and of course, one is the inverse. And then you keep going, and here you have S1 times S2, so the action is on the right, and so on and so forth. And at some point, you might have relations. So two paths which coincide somewhere, which means there are two ways of going here. So this can be made into a metric space. So first of all, I have to define the distance between two vertices, and then I'll add what has to be done on the edges. So I mean, a point here, the point that I've presented here can be obtained by two ways. So there are two ways of writing this element, let me call it gamma, as a product of elements in sigma. And so I write all these ways, and I compute the one which has the least amount of element of sigma. I count this number of element, and this is a number which is the distance between the identity and gamma. Right, so this is a definition. This is so-called word length. And by construction here, it is invariant by the action of gamma on this space, which is an action on the left now. So you let this gamma act on the graph on the left so that it commutes with this action on the right here. But of course, if I stop here, I will have a combinatorial object, and it's more convenient for the rest of the talk to have a one-dimensional graph. And what we do is very simple. We assume that every edge is isometric to the interval 0, 1. And then you can extend the distance to 2 arbitrary points on the graph, right? So it's a very simple graph. But as you can see on the picture, I'm not saying that I am an artist, but as you can see on the picture, you can see the relations in the group. And this is very important. It will be very important in this sequence, right? Okay. So we got a metric space, and as I said, it is very clear for the vertices, but you can check also for the edges. The action of the group on the graph, on this graph, is by isometries. And when you mod out by the action of the group, it means, for example, that you identify all vertices here to a point. So down, what you get is a something like this. So I think even in English, it's called a bouquet of spheres, of circles, a bunch of circles, a wedge of circles. And because every edge is identified to 0, 1, the diameter of this object as a metric space, it's also a metric space, with the induced distance is 1. Sure. No, we don't need a... You don't need a... It's not a directed graph. No, it's just a... Well, so the graph is identified to the interval 0, 1. So the distance here is something. So I don't think it's useful. It's arbitrary. I don't think it's useful here. I don't think it makes a difference. But you're right. One could consider oriented graphs. That's another story. I agree. That's another story. So this is the next step. But next step is for you, because there are plenty of analysts in this room, and the analysis we don't know how to do at the moment. But of course, this is another story. At this stage, we don't need to orient the edges. Are there any other questions? Okay. And the measure is a counting measure. So, I mean, for convenience, we can take the identity element, and you look at its orbit, which is a full group, and you put a delta mass on each of them. But you can take any point here or here and look at the orbit, right? So you see the distance between this gamma to the identity element is the shortest of these two paths, which correspond to the geodesic. Right. Well, okay, so every time you have a marked group, which is a group with a finite generating set, to get a graph. And in the statement that I've shown at the beginning, there was the last sentence was in parentheses up to isomorphism of marked groups, and I have to say what it means, and it means the most simple thing that you can think of. I'm sorry. So here we have two. Sorry. So let me try not to make a mess. Here we have two marked groups, and they are isomorphic. There is an isomorphism between gamma and gamma prime, which sends the generating set sigma to sigma prime. And you can check that this implies that this isomorphism becomes an isometry of the metric space that we have built. It's not equivalent. That is what I want to say, that there are isometries which are not coming from isomorphism, but we don't care. Okay, so here's an example. A very classical example. I'm not very cautious because I stole this on the internet, but it has been on the internet for so long that I figured that it would be. So this is a free group. There are two generators, alpha and beta, and of course the edges, they do not seem to be to have the same length, but it doesn't matter. You can decide that the length here of this blue line is the same than this one. We are mathematicians, right? And when you mod out by the group generated by alpha and beta, we get a bunch of two circles. And this is the generic situation, right? Well, generic, no. So here we have a free group, no relation whatsoever. Okay, let's come to counting. Okay, so okay, so I did not define yet Gromov-hyperbolic group, but in our context, in the statement there was the word cyclic. So in the context we are interested in, cyclic means isomorphic to Z. Right. There is no other cyclic group in the context of Gromov-hyperbolic groups, which I will define in a minute. But if you look at Z itself, then you have several ways of marking Z. So you have plenty of generating sets. And for example, these ones, for each n, you have a generating set. And two of them are non-isomorphic. So the finiteness theorem that I stated is wrong for this situation. That's why in the statement, we had to exclude this case. It's very easy to check. Okay, so let's come back to counting groups. So there is a remark that I should make before going further. If you think, for example, to groups with two generators, if you are just asking that the group has two generators, you'll find infinitely many of them. And it's an exercise for students, right? So the number of generators is not sufficient. So you have to add something which is related to the relations. So the group is said to be finitely presented if it is finitely generated, and if all the relations can be finitely generated as a normal subgroup by a finite set. So what do I mean? Relations are words which are equal to the identity. So they are words in the free group generated by the generating set, the free group in all the generators. And the relation form a normal subgroup. And sometimes this normal subgroup has a finite set of generators, sometimes not. So finitely presented means that this normal this normal subgroup is generated by this curl R, and curl R is finite. So there are finitely many relations which generates all of them. When I said generated, I meant generated as a normal subgroup, which means that any other relation is a finite product of conjugate of the relations which are here. But for the context, for us, it's more than sufficient. So this is the definition of finitely presented group. And the main proposition, which is also an exercise, is to show the following. If you bound from above the number of generators, so the cardinality of sigma, if you bound from above the length of the relation, then you get finitely many groups which satisfy these two properties. And you can even estimate. So it's really an easy exercise. Because if you look at relations which have length less than p, then you cannot use more than p elements of the generating set to construct this relation. So there are finitely many. And you play this game and you get the answer quite quickly, right? But this answers the question that I asked at the very beginning, how do we count groups? And now we have somehow an answer. The goal is now clear. We have to estimate these two numbers, cardinality of a generating set and the length of the relations which generates all relators in the group, right? So let's go a bit further. Okay, so now I have to define this notion of hyperbolicity. So I'm pretty sure that all of you already know, but let me go slowly again. So a metric space, which is geodesic, is said to be delta hyperbolic if all triangles are delta thin. And sometimes if there is another word for instead of thin, I don't remember. It doesn't matter. So what do we mean by delta thin? It means this picture, which I also stole on the internet as usual. So what is a triangle? Take 3 points. The space is geodesic, so there are geodesics between these points. So you get one triangle by choosing geodesic between the points 2 by 2. You might have several. And the condition which is here is that it should be applied to all triangles. And what is delta thin is it means that any point on this edge here, is a distance less than delta of the union of the two other edges. So the triangles have this shape, you see, very thin in the middle. Okay. And well, you imagine that the space is locally compact. So if you look in balls of radius 1, this will always be satisfied. So this is more difficult for big triangles. Yes, of course. So every point on one side is a distance less than delta of the union of the two other sides. And of course, in all sides and for all possible triangles. So an example where it's not satisfied is R2. If you take big triangle, there are points which are going far away, going to infinity. The distance to the other side is going to infinity. So it's really a notion which corresponds to negative curvature. That's why it's called hyperbolic, right? This is a classical joke in France. I mean, Bourbaki, you give a definition, and the first thing that you show is an example where it's not satisfied. So this is ridiculous, right? And well, place where it's satisfied, if you are familiar with two-dimensional hyperbolic geometry, then the triangle has this shape, right? Even the triangles with point at vertices at infinity, right? So the name hyperbolic makes sense. So it's definition which is due to Gromov, and here you see the second number that appeared in the statement, right? So for the Riemannian geometers, I'm thinking of curvature being negative, and so this delta is a distance, whereas the curvature is usually the inverse of a distance square. I mean, as a physical dimension. And so if the curvature is negative, delta square behaves like 1 over the absolute value of the curvature. In other words, if the curvature is negative, delta gives the existence of delta says that the curvature, sectional curvature in that case, is bounded away from 0. It doesn't go to 0. And furthermore, if delta goes to 0, then the curvature has to go to minus infinity. I'm thinking of a case where the curvature is strictly negative everywhere. Minus infinity corresponds to the case of trees. One can show that if the zero hyperbolic spaces are trees. And if the curvature approaches 0, then delta has to go to infinity. So somehow R2 is infinite hyperbolic, which means not hyperbolic at all. Right? So you keep this in mind. This is another coarse version of the curvature. And I want to play with these two coarse versions of curvature. Entropy, which corresponds to a lower bound. Delta, which corresponds to an upper bound in the case of negative curvature. Yes, you can. I'm pretty sure I didn't do the exercise. I'm pretty sure you can prove that with an upper bound on the curvature. If it is negative, you can prove that there is a delta which you can compute. You see, the first step is to compute the delta for the two-dimensional hyperbolic space, which is something like log of 3 or something like this. And then by comparison, you get a formula. But of course, this is in the case where the curvature is strictly negative everywhere. All right? And that I already said. And what is important is that in this context, the invariant that we are using, they don't say anything about the local geometry and even the local topology. So you might perturb the space locally, even the topology of the space locally, and keep this delta on for large triangles. And we'll see this later. Right. I'm sorry, this is very low. So let me read this for you. A marked group gamma sigma is delta hyperbolic if the Cayley graph with the distance that I have defined, or not defined, but shown, is delta hyperbolic. So this Cayley graph, which is a metric space associated to a marked group, gives a notion of delta hyperbolicity of the marked group. And so this explains half of a sentence in the statement. Let me go a bit further. Now we can say that a group is hyperbolic if there exists sigma, so that gamma sigma is delta hyperbolic. And of course, the number, the number delta depends on sigma. If you change the sigma, as long as you stay within a finite generating set, you change the delta, but it will not go. It will not go to infinity. So the notion of hyperbolicity for a group is defined without delta. It's not possible, but if you want to have a delta, you have to choose a generating set, because then you get a metric space. And then for the metric space, you can apply the definition that I have mentioned before, right? And this proposition is famous and very easy to prove. And I will not prove it because I will be running out of time. But it's a classical thing. You see, delta hyperbolicity has something to do with relations. So if on the picture that I have drawn here, there is a triangle. For example, this is one side, this is another side, and this is the third side. So the triangle being thin means that it's not like this, because if you go further away, so it means that you must have very special relations in your group. And it's very difficult to say, well, it's not very difficult. Some people know how to say delta gives some kind of particular kind of relation, but it's not the purpose of this lecture. And so if gamma sigma is a marked delta hyperbolic group, it can be presented with relations of word length less than 4 delta plus 6. It's not optimal by no means, but it's important. This delta governs the length of the generating set for the relators. Right. So now the goal is clear. If we can bound the cardinality of for a delta hyperbolic group, for an hyperbolic group or a delta hyperbolic marked group, if we can bound the cardinality of the generating set, then we get finiteness. Because in the previous proposition, which counts groups, we can use this as a second tool, and so the only thing that is left is to control this. And so far, delta has played a role, but this entropy has not played a role. So we have to bound the number of generators. So we have to show that there is a generating set, so that the number of generators is bounded by this asymptotic invariant. So it's like computing the volume of a ball of radius 1, for example, knowing the asymptotic. In general, it's impossible. So why should it be possible here? So let me try to explain this. We are in a very specific context, the context of this delta hyperbolic marked group. Okay. So now comes geometry again. So there is a classical proposition which you can find in the book by Serre on trees, and what we usually call Gromov's green book. Oh, it's not Brook, it's book. I should correct this. Well, why green book? Because it was green, actually. The first version was simply green. He gave a course at École Normale in 1980, and the notes were published, and the book was green. And in this book, he addresses some of the questions that I'm discussing today. Right. So the book is metric properties of Riemannian and non-Riemannian spaces, or something like this. And it opened a wide area of research. I mean, it's amazing. And then he published a new version where he added a chapter that is more than 150 pages. And I would recommend to read the first one, I mean, which is more adapted. And so this proposition is also very classical. And in Serre's book, he attributed to Macbeth. Well, and there are other people who have been doing this. So you take here like simply a path-connected space. You don't need geodesicness. and you take a subgroup of the isometric group which acts on this path-connected space, and you ask this action to be proper. So the action being proper means exactly that the orbit is discrete. So you can count points in. And you look at the element of the group, excluding the identity element, whose displacement at x for any x is less than twice the diameter of the quotient. We assume that there is a compact quotient whose diameter is less than d. Then this is a symmetric finite generating set, which is symmetric, obviously, but it's finite. Right. So I wrote right. So it's very classical. Maybe I don't give the proof. I wrote the details of a proof, but it might take some time. I want to reach a more interesting point, and it's classical. I think Serre has a proof which is without using distances even. So it's worth looking at it. So what is the cardinality of this sigma 2D of x? Well, we are using counting measure. So the cardinality is the number of points of the orbit inside this object. It turns out that this is the measure, the counting measure centered at x, related to the group gamma, of the ball centered at x and of radius 2d. And because of this non-strict inequality, it's a closed ball. So the thing we have to do is, as I said, is control the volume of this ball in terms of the asymptotic invariant, which is the entropy. Right. Okay, so this is a sketch of proof, but really I can explain after. I mean, if you want to drink a beer, I can explain easily. It's not worth spending time on it. And if you go through the sketch of this proof, then you can prove also the 4 delta plus 6 in the same way. Well, anyway, let me state the main results. I need to keep some time to discuss the main results that we are using, the main tools, because they are somehow, well, I find it interesting. I should not say so, actually. Okay. So the main result is this. So if you give yourself delta H and D, delta could be 0, but let's say it's strictly positive, and take a subgroup of the isometric group of the of a space XD, which is supposed to be delta hyperbolic. So delta hyperbolic implies that it is geodesic and proper. And I forgot to say that the subgroup is discrete. We assume that there is a compact quotient whose diameter is less than d. We can compute the entropy, and we assume that it's less than h. And we assume that it's non-cyclic and torsion-free, as it is in the first theorem that I stated at the beginning. Then this is the generating set. Of course, because this 10d plus delta is greater than 2d. Sigma 2d is a generating set. But for sigma 2d, I'm not able to compute the number of elements. And if we go a little bit further, then we have tools to compute the number of elements in this set. So the number of points of the orbit in this set, and estimate them, estimate this number in terms of delta H and D only. With 2D, we are not able to do it, so we enlarge a little bit the bound, and the balls, closed ball of radius 10 times D plus delta around any point X have a cardinality with respect to this counting measure. So the cardinality of the orbit in this ball is bounded above by some number, which depends on delta H and D. And the number is almost explicit. So I will tell you where the almost comes from. Right. And so we have finished with the delta hyperbolic groups. Why? You apply to a delta hyperbolic Mark group, which acts on its Cayley graph. So the diameter of the quotient is 1. And if we assume that the group is delta hyperbolic and that the entropy is bounded above, as it was in the statement of the first theorem, then we can apply this bound, and delta H and D can be replaced by 1. And so we have a control on the generating set. And if we have a control on the generating set, because we have a control of the length of a generating set for the relators, we get finitely many such Mark groups. Right. So applying just this result to the situation, and we finished the proof of the theorem that I stated at the very beginning. But this shows that it is part of a more general situation. The context is much wider than computing the number of groups with some properties. And the context is about very special metric spaces, which are delta hyperbolic, and very special subgroups of the isometric. So this is not an easy theorem to prove. What I can do is to explain the two main tools that we have been using in proving this result. And they seem to me interesting. Do you have any question at this stage? No, because we have to deal with the entropy here. So indeed the entropy is no, the entropy is not the problem. The problem is the delta. So the fundamental group is delta hyperbolic, but you have to control the delta. Yes, but the delta of the fundamental group is not always the same. I mean, depends the way it is the orbits is in the group. So it does not say directly what you're saying because of this. We have to. So you look at the simply connected hyperbolic space, and you look at group acting on them, and you have to compute the delta of the group independently of its action on the space. The delta is given by the action of the group on its Cayley graph. And so so the answer is yes, if you add this information, which is the delta coming from the fundamental group, which is not easy to control in this situation. Okay, so let me give okay, so this is something I've already said. So how much time? 10 minutes or something, or a little bit more than 10 minutes, right? Okay, good. Let's talk. Good. So let me show you the two main tools. So what we have to count is somehow the volume of a ball of a radius, which is given by this fancy number. And this is by no means optimal. Just we made some computation, and this is a number which turned out to be the most convenient in the story. And again, I'm insisting on this fact: we have to compute the volume with respect to this measure of these balls, knowing the asymptotic volume. So we have to make a relation between them. And so next theorem is one of the key tools. So there are two key tools, one coming from our work and one coming from other people's work, and I want to explain both of them. So here is the main theorem that we have been proving, whose consequence is what I've been saying during this lecture. If we start again with a metric space, which is delta hyperbolic, we take a discrete subgroup of the isometric group, and we assume that the diameter of the quotient is less than D, and the entropy of the space is less than H, right? And then we have a control on the ratio of the volume of balls. So the volume of a big ball, so it's closed here, but it doesn't matter. You can forget about this. Divided by the volume of a small ball centered at the same point. This ratio is controlled by some number. So forget about the 25/4 and the 3, which are not optimal. What we have to check, first of all, is that this is dimensionless in the sense of physics. So this is a ratio of two distances. And the entropy is not difficult to check, that behaves like the inverse of a distance. So H times R is dimensionless also. And so you see the control is not too bad for a situation which is quite general, because we have almost H as exponential growth. Well, the price to pay is that we have coarse definition of curvature, so we have absolutely no information about the local geometry and topology. And this is reflected in this result by asking that the two radii are big enough and bigger than this quantity, which depends on the diameter and on the delta. So for the Riemannian geometer, this is an instance of Bishop-Gromov inequality. Ratio between, you centered at X and you look volume of a ball of radius capital R divided by the volume of a ball of radius small r centered at the same point. So Gromov proved that there is an inequality when you assume a lower bound on Ricci curvature. And here we don't have lower bound on the Ricci, on the Ricci curvature, but we have entropy, which replaces lower bound on the Ricci curvature. So that's where we can control. So we don't control the volume of a small ball with respect using the entropy. We control this ratio using the entropy, which at the moment is not sufficient for our purpose. Okay, so if you, okay, I'm selling my goods here. If you think to Bishop-Gromov for the Riemannian geometer, if you think to Bishop-Gromov inequality, it has been extremely useful when one considers limit of metrics of a Riemannian manifold. So if do these experiments, thought experiment, you withdraw from Riemannian geometry this Bishop-Gromov, so you lose all the convergence properties, and hence you lose Poincaré conjecture and you lose geometrization because Perelman used limits all the time. And so this is just a minor change in the comparison theorem that Gromov has made in the past, but this has consequences on the long term which are amazing. Right? So this control of ratio of volume of ball was very important for Riemannian geometry. I'm not saying that it is as important here, but who knows? Maybe later. So it's what I want to say is that it is useful. Furthermore, what we are controlling here, this counting measure. So we have a version where the measure is not counting measure, but counting measure means number of elements of the orbits in a ball of radius r. And if you are familiar with this question of looking at group acting and at counting number of elements of the orbits, it's not easy in general. And it's not easy for one ball, it's not easy for a ratio either. But this will help doing the proof of the main theorem. Of course, it's not true for smaller radii. It would be it would be wrong anyway if it were true for smaller radii, for the reason that, as I said, we have no information whatsoever about local geometry and topology. So this is the best way to motivate it. Surprising Bishop of type inequality. It was surprising. So now I start the scatter proof of the main theorem, and we'll come to another tool which is also where I find amazing, and it's due to 3 other people. So let's start the proof. So for the sake of simplicity, we'll call this fancy number R0, and what we want is to count. To measure the volume with this counting measure of sigma R0 of X. We'll take a little bit of room to do some computation, and we'll take sigma 3 R0 of X. So the element of a group whose displacement at X is less than 3 times this number, 30 d plus delta. We don't care anyway, because you can put 30 or 100 or whatever, right? And we compute. So this is a subset of gamma. of the group of isometries that we have been taken. And we compute A times A, which is just the set of products of two elements which are in A. Right? So it's a notation. And it's not difficult to check that this, because the displacement of each of them is 3R, the displacement of the products by triangular inequality is less than 6R0. So it's included in a closed ball of X1, right? And why are we doing this? Because now we can apply our result and get this inequality. So the cardinality of A times A divided by the cardinality of A, well, is bounded on the numerator, it's just less than the measure of this ball. On the denominator, it is equal or is greater because it should be a closed ball. So cardinality of A is greater than the measure of this ball. And so we get this inequality. And now we know how to control this in terms of the data, which are H, D, and delta. This is given by our result, right? And this is a number which I call K. But this, for those who are familiar, is some kind of doubling property. It means that if you keep doing these products, A times A times A, A times A times A, and so on, then the number of elements is growing polynomially. And we are in context where we are rather in negative curvature. So this says something about the size of this set. Right, this is doubling property for those who are familiar with this. And yeah, sorry. Okay. So this is where our result comes into play by controlling this, right? So what is the next tool? Next tool is a beautiful theorem by Breuer, Green, and Tao, which I want to comment now. Yeah, I still have time to comment it. You give yourself a k, which is greater or equal to 1. Then there is a number nu of k, which is an integer. So far, it's okay, right? And the properties of this number, so far we can, everybody can prove that, right? The property of this number is amazing. If you pick any group G, so any group, we are not asking to be discrete, we are not asking to be delta hyperbolic, we are not asking anything. And if in this group, there is a finite non-empty subset which satisfies this kind of inequality, then this subset is small in the sense of group. And what does smallness mean? It means this fancy proposition, there exists a subgroup G0 of the big group, G, and a finite normal subgroup N0 of G0 such that A is covered by nu, at most, nu of K left translate of G0, and G0 is nilpotent. Well, it's not true. G0 is almost nilpotent. So I mentioned for one previous slide that this doubling property corresponds to polynomial growth. It's not exactly correct, but let's forget about the details. For groups, polynomial growth implies nilpotency, or almost nilpotency, by the theorem of Gromov. But A is not a group, just a set, finite set. And we don't have polynomial growth. Well, we have just this. And if you keep doing the products of A by itself, you don't get a group a priori, right? And so that's why A is not nilpotent or almost nilpotent. A is covered by finitely many translate almost nilpotent group, right? And this is amazing because for every K, there exists nu, satisfying this for every group. Right? And in our case, we apply this to our case. We have the set, exactly the set we want to control. So the group is, well, I call it gamma. So let me assume that G is equal to gamma. Is a torsion-free hyperbolic group. And it turns out that, well, torsion-free, this finite subgroup does not exist because that would imply some torsion. So it's the identity. So G0 has to be nilpotent. But then in a hyperbolic group, nilpotent implies infinite cyclic. So it's a classical fact also. And so G0 is a cyclic subgroup of gamma, which I call gamma cyclic. So, I mean, if I will use this board again for the second time. So here's the ball that I want to consider, this 10 times or 30 times d plus delta. There's a point x, and I look at the translate. Gamma 1 of x, gamma 2 of x, and so on and so forth. Well, if you look at this gamma 1 of x, it generates a cyclic group, gamma 1 square, gamma 1/3. So the cyclic group I will draw here. And this one generates a cyclic group. And this one also, and so on. So being able to cover a ball by a union of cyclic group is not difficult. It is always true. But the point here is that the number is controlled by a universal bound, and this is deep, right? Okay, then we just have to play with the whole situation. So I have 2 slides, but the second one is a bit technical. Let me just give the next one, and then I stop, or maybe I stop here if you wish. You don't answer. So okay, let me. So the way we proceed, I show you the way we proceed, and there is an extra lemma which I will not prove because okay, let's say I'm tired for the lemma. So we start with this space, with this set A, which is the element of gamma whose displacement at x is 3 times R0. Again, the 3 is just here to have some room to do some computation. And then there is a new. We found a k, which is given by our Bishop-Gromov inequality, and then associated to this k, which we can assume to be greater than 1, there is a nu of k, which says that this sigma 3R0 of x is covered by, at most, mu translate of a cyclic group. Well, let's say it's exactly mu, because otherwise what I'm going to say is wrong. But we can adapt the situation. And this is larger than this set here, of course. And well, and we may also choose the gamma I to be inside here. This is not true. This is where I'm cheating. But let's forget about this. So in order to compute the cardinality of this set, we have to compute the sum of the cardinality of these sets intersected with the sigma R0 of x. This is trivial, right? And there is another trivial remark that if G is here in this set, then gamma I minus 1G is in this one. Well, if you multiply on the left by gamma I minus 1, then the displacement at x might not be R0. But if you assume that gamma I displays less than R0, then the triangular inequality gives you this 2R0 here. It's for this kind of computation that I choose some, that I kept some room, right? And so we just have to estimate this. And then we multiply by nu. And here there is a trick. So the trick is to, amazingly enough, I mean, we want to compute the number of points in this set. We will enlarge it, which is not a good thing to do, but in that case, it works. So there is, in the situation where we are, anytime on a delta hyperbolic group, one has a cyclic group, there is a maximal cyclic group which contains a maximal one. And so I'll call this maximal cyclic group as gamma sig hat. And so the lemma, which I don't want to explain because it would be a bit tricky, is that even if you enlarge this object to this one, because of course maximal cyclic, there are more elements than in gamma cyclic, then the cardinality is bounded by nu. And why do we use the maximal cyclic? Well, if the cardinality is greater than nu, it means that there are 2 elements in this object which are in the same left coset. And playing with this and maximality, we get a contradiction. I can explain this privately if you wish. And then this is done. And then, so every element here has cardinality less than nu. There is at most nu, so we get a bound like nu square. Okay, so these are issues which are not that interesting for you at the moment, and we just have to remember the general scheme. I mean, we use this Bishop-Gromov inequality to show that this set A satisfies a doubling property, and we use the Breuer-Green-Tao beautiful theorem to show that then this A is covered by a small number of cyclic group, a small and universal number. And from that, just a computation after that. Okay, so I hope I'm ready to answer any question. Thank you very much.
The beautiful talk. Are there any questions?
Yes.
Where is it? Somehow, is it possible to understand where you use the fact that the group is not cyclic?
It's in the last slide. Yes.
This one, you mean? Okay, good.
So you want me to describe this slide here?
Just to get an idea.
Yeah. Okay. So it's in the proof of the lemma here. The lemma means that if you extend the cyclic group to the maximal cyclic which contains it, then you get a same bound. So we'll proceed by contradiction. Assume that this is not true. So if it is not true, we pick an element in sigma 2D, which is, I recall that this is a generating set. This sigma 2D is on the side. We pick an element, and it's not difficult to show that if this is greater than nu, then this one also is greater than nu. The cardinality is greater than nu. Because anytime you have an element here, you get an element here. But of course, the displacement, because you multiply on the left and on the right by S and S minus 1, is a little bit more than the previous one. And 3R0 is okay. Here it's 2D, but here R0 is 10 times D plus delta, right? So let's look at this. Then we have shown that for any generators, well, there is a family of generators here. For any generator where the cardinality of this, which is greater than this universal number nu, right? Which means that you can find two elements which are in the same coset. Gamma I, translate of the cyclic group gamma sic, right? And two elements in this space. Then you just have to write this long sentence, G minus 1 G prime is inside here because you are multiplying two elements which are in this group. And because you kill this gamma I, it's also in gamma sic, right? And then you can go, everything is trivial actually if I speak slowly. So this group is larger than this one, so this inclusion is obvious, right? And so it means that this and this intersect. And the conjugate of a maximal cyclic subgroup is also a maximal cyclic subgroup. And in a delta hyperbolic, in a torsion-free hyperbolic group, two maximal cyclic subgroup, they either are disjoint or they coincide. Well, if you have an element in the intersection, then you have all the powers of this element. So at least one of the maximal cyclic contains the other, but of course by some kind of reciprocity, they coincide. So it means that for any generator in this set, which we know that it is a generating set, but we don't know how to count the number of generators, then this maximal cyclic subgroup is invariant by the conjugacy. But of course, this is a generating set, so this will be true, this equality will be true for any element of the group. So this maximal cyclic subgroup will be normal in gamma. We are in a context of negative curvature. So in these delta hyperbolic spaces, cyclic subgroup of fixed 2 points at infinity. And if gamma sic at is normal, it means that also gamma fixes the same 2 points. And so gamma is also cyclic. it's not possible that gamma is called elementary, but in a delta hyperbolic group, it means cyclic also. And that's where the assumption comes into play at the very end of this sentence, right? This is a contradiction. And this is a trick to which explain why, well, there might be other proof, but this is a trick which explains why we have to go to this maximality. Maximality gives some information.
More questions? Actually, have a
question.
Oh, yes, I do, but yeah. Okay. No, please.
So the number is, I mean, the bound on the number of groups, is it effective in some sense, at least if you know
The new of K.
Yeah.
No,
okay,
it's
so if you
not.
take nu as a known function, fundamental function.
No, unfortunately not. That's where we lose. That's exactly where we lose the explicitness of the bound.
But only there.
Only there.
So if
The
you
rest
use
is
that as a known function, it is.
Yeah. In our Bishop-Gromov, we struggle to have explicit formula, but I mean, of course, it's not optimal, but it's explicit. In the new from Breuer, Green, and Tao, it's not explicit. But maybe we should look at the proof more carefully and do something, but it's tough. So that's where we lose explicitness.
Do you have examples showing that there are many such groups?
Many such.
Well, I mean, that's an upper bound, right? What do you know about lower bound?
If you relax, yeah. There are plenty of examples. If you relax the assumption on delta hyperbolicity, then you might have hyperbolic group whose entropy is bounded by H, which accumulates. And for example, you can think, so the good picture to have in mind is what happened for hyperbolic manifold in dimension 3. So if you look at closed hyperbolic manifold in dimension 3, and if you compute the volume, then if you look at the volume, Thurston described the structure of this set of volume. The volume could go to, I'm sorry, I have to do a correct sentence. You could have a sequence of closed manifold which converges towards an open a manifold with cusp, and the volume has a limit, but it always converges from below. That is, the volume increases, well, up to some. Being careful. And here we have the same situation. So it was proved by Fujiwara and Sela that you could have a sequence of hyperbolic group whose entropy is bounded, but which converge to a group which is not anymore hyperbolic. And the reason is that along this convergence, the delta goes to zero. No, to infinity. I'm sorry, to infinity. So there is some flatness coming into the story. So there are examples of such a situation. I would not be able to give you a precise example, but they do exist. It's related, and I don't know if I would be able to prove that. I mean, in the case of hyperbolic manifold, we can show that the limiting manifold is a manifold with cusp. So that the fundamental group of manifold with cusps is not hyperbolic, but is so-called relatively hyperbolic. So in that case, some people say that we could prove that it is relatively hyperbolic, but nobody knows precisely a proof. So it's still something to be understood. But this corresponds to Den feeling, yes.
Actually, I have a question. So the Bishop-Gromov inequality you stated is not sharp, but presumably.
No,
but could one possibly imagine like a rigidity statement in this context?
So what kind of rigidity?
Because if you have equality for Bishop-Gromov, then you have what, constant curvature?
I don't think so, because you have freedom to modify your space locally, and even the topology. You have complete freedom locally. That would not change the hyperbolicity. So you might be able to say something about the long range.
Yes, yeah.
behavior. And this
that's-
I don't know.
yes.
This I don't know. I'm not sure that we can do that because it should be sharp somehow, but it's not, even in the long range. But that would be nice, yeah.
Okay, so I guess we're done with the questions, so we can thank
Thank you so
Gérard
much.
again. Thank you.